Hi class, hope you're well. Today we are going to talk about intermolecular forces, which I know is something that a lot of students struggle with. And it's something that I focus on quite a lot in grade 11 because of how important it is in grade 12, biology, chemistry, and beyond. And you know how much I love biology, and so I really want you guys to understand this. So let's do a quick recap about intermolecular forces. And I like doing this scale. And I'm going to go from the bottom, from the weakest. So these are the weakest intermolecular forces to the strongest. Now, intermolecular forces, let me just review what those are. Those are the interactions between molecules. Okay, so let me just explain it in terms of intra and interpersonal skills. So if you have intrapersonal skills, it's the relationship you have, with yourself, how you view yourself, how you think, etc. Interpersonal skills is how it's your relationships, it's how you act with other people. Remember those two things when you're dealing with intramolecular forces. So that is ionic bond, polar, nonpolar bond. It's the forces within a molecule. And then intermolecular forces. It's how molecules react with other molecules. Hopefully, you guys have been cooking. Hopefully, you guys have been making some delicious recipes over this quarantine. And you might notice that when you mix two substances together, they don't want to mix. Okay, that's all based off intermolecular forces. Make some pasta. You boil water, you put in some oil. That oil does not mix. Okay, it disperses itself, especially at higher temperatures, but it does not mix. And that's because oil is nonpolar, water is polar. The intermolecular forces do not allow those two molecules to mix. Okay, you can start seeing so many things in the world in a different light when you have an idea of intermolecular forces. Okay, so the weakest I was talking about, nonpolar molecules. Let's go all the way down here. You guys, I've drilled this into you guys. You guys know that London dispersion forces are the weakest type of intermolecular forces. And so London dispersion forces, they are the syncing up of electrons. And so every time, every single polar bond, or sorry, every single covalent bond is, oh my goodness, so many notifications. It has LDF forces, whether it's in polar or nonpolar. So the bigger the molecule, the more LDF forces. So if I was to draw a molecule like methane, and then I'm going to draw another bigger molecule. Okay, this is a hydrocarbon, hydrogen and carbon. Okay. Both of these, they have multiple covalent bonds. And so, and they're they're non-polar. And so the only forces that they exhibit are LDF forces. Now this methane is going to be gas at room temperature, whereas this bigger molecule, that's butane, is going to be liquid. And the reason why there's a difference between gas and liquid is because the bigger the molecule, the more LDF forces, the more cohesion, the more they're going to interact with each other. So because there's more interaction in my butane, it's going to go from gas to liquid. LDF forces, they're in, like I said, every molecule, but they're mostly they're the dominant force in nonpolar molecules. Let's go up to the next one. Now, I'm going to explain both of them at the same time. Let's see how my thing's looking. Both of these are dipole-dipoles. So both dipole-dipole forces. But you guys know that there's one type of dipole-dipole, hydrogen bonding, that is capable of more intermolecular forces than just a simple dipole-dipole. Dipole-dipole. Okay, so let's explain hydrogen bonding before we move on to dipole-dipole. You guys hopefully remember that it's only when you have hydrogen and oxygen bond, hydrogen and nitrogen bond, and hydrogen and fluorine bond. So if you remember the activity where I got you guys to highlight different molecules for the hydrogen bonding, just a regular polar bond or non-polar bond, that's how I analyze big molecules, because I want to look for these three. Now, do you guys notice this is just a halogen? This is hydrofluoric acid. You don't really see hydrogen fluoride. So really, my eyes are trained to look for oxygen, hydrogen, and nitrogen, hydrogen. Now, one thing, or you know what, I'm gonna draw two molecules. I'm gonna draw this is ammonia. Okay, so do you see how there's NH bonds? So this is a very polar bond. I'm going to show my polar bond this way. Okay, and it's a hydrogen bond because it's nitrogen and hydrogen. Okay, I'm saying it's a hydrogen bond, but what I really should be saying is that it's capable of forming hydrogen bonding, because hydrogen bonding is an intermolecular forces. I'm looking at just one molecule here. So I'm analyzing the intramolecular forces, the polar bond, which happens to be between nitrogen and hydrogen, that is capable of making hydrogen bonding. Let me draw another molecule, one that you should be very familiar with, that's capable of making two hydrogen bonds. Water. Okay, so it's an OH. I have NH and I have OH. That's pretty much all you're going to see. I like to draw dotted lines, much to the dismay of students because they get confused by it, but I'm sorry, that's just, chemistry, whatever. This hydrogen here is going to be forming hydrogen bonds with this oxygen. So there's going to be an attraction force. This nitrogen is also going to be attracted to these hydrogens. Again, that looks terrible. So the way I would really orient the molecules, let me redraw this. If I have a nitrogen, how would they orient themselves? Well, the hydrogens of the water will want to be close to the nitrogens. Okay? And then here, the oxygen is going to be attracted to the hydrogen. So I'm going to start putting in dotted lines. Do you see that OH? Okay. That is a hydrogen bond. Why? Because this oxygen hydrogen, that is one of my special type of hydrogen bonds. And this nitrogen and hydrogen is that special type of bond. So because of it, this bond right here, that intermolecular force, can form. And because it's from two different hydrogen bonds, we can say that that's hydrogen bonding. I know it's kind of confusing, okay, but this is the easiest example that I can show you. So always analyze your molecules and look for NHs and OHs. And when you see that, you can say, aha, I can form hydrogen bonding through that. Okay, dipole-dipoles. Dipole-dipole is for anything left over that is going to have a dipole but is not as strong. So for instance, you could have PH3. Okay, so that's a polar bond, but it's not as strong of a polar bond as my as my hydrogen bonds. Okay, and trying to think of other ones. Anything with sulfur as well. So sulfur, like that. Okay. Review your notes from Unit 1. Gosh, I'm writing terribly. I apologize. Now, okay, so LDF is for nonpolar. Dipole-dipole forces is with polar molecules interacting with each other. And then this one up here, which I did introduce you guys to, and I said that we would talk about later. This is ion dipole interactions. So you remember that there's this scale for electronegativity. You can go from 0 to 0.5, that's nonpolar. 0.4 to, look, I say 0.5 and then I write 0.4. It's in that range, right? It's all scale, it's all relative. And then about 1.7, we have polar. And then 1.7 to 3.3, we have ionic. If you are, okay, so a normal dipole-dipole bond is going to be in like this range here, okay? It's very weakly polar. So the intermolecular forces, it's not very strong. Hydrogen bonding is going to be over here, okay? So as you move over to this section, then the more you move to 1.7, the stronger the intermolecular forces are going to be. But then something interesting happens when, say, you have a hydrogen bond and it starts interacting with an ion. Okay? When you have an ion and a hydrogen bond, or an ion and a dipole, then there's going to be more interaction. Okay, so let's look at an example. Let's say we have sodium chloride. Let me switch this up. You guys know that it's sodium plus and chloride minus. And I'm going to put it in water. If you did my practice test, you would have seen that there was a question about this interaction and what happens. And so the correct answer is that a sphere of hydration occurs. And I'm going to show you what I mean by that. This is, pretend that this is an ionic bond. And I dissolve it in water. So now they are dissociated, is a word I want you to learn for grade 12. Dissociated, or you've broken the ionic bond. I'm going to start drawing water. If sodium is positive, it is going to be attracted to the negative dipole of water. So I'm going to put, oops, is it hydrogen or oxygen? I was just about to draw oxygen. No, the negative dipole is the more electronegative of the elements. It's going to be water. And so if you arrange the water molecules so that the oxygen is facing the sodium, do you see how a sphere starts to naturally be created? Okay, all of the oxygens are encircling the sodium. It's not the hydrogen side, it's the oxygen side. So, and since it's a sphere of water, we call it a sphere of hydration, or hydration sphere. Now, same water molecule, I'm just going to use a different color. If it's around chlorine, chlorine is negative, it's an anion. It's going to be attracted to the positive dipole side of water. It's going to be attracted to the hydrogen side. Now, water has two very strong dipoles, right, from the oxygen and hydrogen. So we know that there's a high level of difference in electronegativity. And then chlorine anion and sodium cation, they are both very, very positive and very, very negative. So this attraction force is very strong. And you can try this just by putting normal table salt into water, and you'll see that it'll dissolve. Okay, the way that it's dissolving is it's breaking apart this ionic bond because of the spheres of hydrations that it's forming. If you keep on adding more and more salt to it, okay, eventually what's going to happen is you're going to reach a saturation level, and there's just not enough waters to form these spheres, and no more sodium chloride would be able to dissolve into it. Okay, so that is the little review of intermolecular forces. And it's important for looking at solubility because of like dissolves like. Okay, so I've heard this a million times, and so I understand it. But for somebody who's just now seeing this, what does it mean? Okay, so like dissolves like. What we're really talking about is nonpolar solvent versus polar solvent. Now, ionic compounds are always solid at room temperature. And so we never look at, okay, what can dissolve in ionic compounds, because that's just not something that we need to discuss, okay? Because if you remember from our lab, they have very high melting and boiling points. They're all solid at room temperature. Whereas when we're in this unit, solutions, we're looking at usually liquids. Okay. Yes, we can look at gases, but usually liquids I'm going to talk about in this unit. Next unit is all about gases. So I'm looking at what can dissolve into a nonpolar solvent that is liquid. Think about oil. What can you mix with oil? You can mix other oils. Okay, so that is because nonpolar dissolves nonpolar. Okay. Polar substances. Okay. Polar dissolves polar. And then polar dissolves ionic as well. You're saying, okay, why? Let's look through at what intermolecular forces allow this to occur. Nonpolar only has LDF. So it's the LDF forces interacting with the LDF forces. Polar dissolves polar. Okay, well, now we can either have dipole-dipole forces between the two molecules, or you can have hydrogen bonding between the two molecules. So because of those stronger interactions, you can think about it. What's going to be more soluble? Like what can you mix more of into what? Can you mix more polar solvent in polar solvent, or more non-polar solvent in non-polar? Well, because dipole-dipole and hydrogen bonding is a stronger intermolecular forces, you can mix more polar with polar. And then finally, polar dissolves ionic. This is going to be the ion-dipole interaction. And that's where you get things like solubility curves. You guys know that most ions are soluble in water, which is a polar solvent, and you can actually get quite a bit of most ions dissolved in a 10 gram or 100 gram sample of water, and that's because of these very strong ion dipole interactions, which results in a sphere of hydration. Okay, I gave a question. I wanted to see who could do this. I gave a question about, let me draw it, my terrible drawing skills. Here's my little rainbow cup. Oops. And I had one liquid, two liquids. Let's do a highlighter liquid, 3 liquids. And I said, what could this combination be? And one of the combinations could be that this was polar, this was nonpolar, and then this was polar again, or that this was nonpolar, this was nonpolar. Basically, you're sandwiching something in between that isn't that's different than the other two. So whether the top and bottom are polar, in the middle is nonpolar, or the top and bottom are nonpolar, in the middle is polar. That's a mouthful. Okay, there is another little trick answer to that. And one of the other trick answers is they could all be nonpolar. And you're saying to yourself, Ms. Vella, you just said like dissolves like. If they're all nonpolar, won't they all just mix together? Okay, yes, you can shake them up. And then if you have ever mixed two different oils, they do mix together, but they form these little spheres. And if you let them sit together, if you let them settle, what happens is that they separate based off of density. And the reason why they separate based off of density is if all they have are LDF forces, all they have are LDF forces, that is a very weak interaction. It's a very wimpy interaction. Simple gravity is going to separate it. And what is it going to separate it based off of? Density. Okay, this is going to be the most dense. This is going to be the least dense. This is going to be the biggest molecule. This is going to be the smallest molecule. All right. You also have to separate based off of density if it was just polar and nonpolar. But this is one way where you can have all three nonpolar substances in one, I think they call it a density tube, and they won't mix. It's because the LDF forces just are not strong enough to interact with each other permanently. Whereas think about salt in the ocean. If you have salt in the ocean, if we go back to the sphere of hydration, we have no risk of our oceans becoming unsalted because it's going to separate out. And that's because this very strong intermolecular force called ion dipole interactions, that all of the salt, all of the ions that are dissolved within the ocean are going to be permanently put into spheres of hydration. How could you get the salt out? Well, you'll have to boil off all the water. And that's how we get, did you know that all the salt in the world originally came from the sea? There's no other way that we can get salt. Yes, we mine salt like the Himalayan pink salt and things like that, but all of it originally comes from the sea, comes from the ocean, and then it's the water is evaporated from it. Okay. I hope this helps you guys out. Just one more thing to talk about is how you can make things dissolve better. And think about, let's go through. One of them is surface area. All right, is it easier to dissolve a chunk of ice, or a chunk of salt, or salt granulized particles? Okay, hopefully, I keep on saying, I hope you guys are cooking, I hope you guys are baking. I do. Think about when you have a salt grinder. You grind the salt so that there's more surface area, so that it dissolves better in the food that you're cooking. It's the same in this unit, in chemistry. The reason why is because if you were water particles trying to form a sphere of hydration, you have to start working on the outside and then think about all the salt inside the middle. That's going to be very difficult to form spheres of hydration until you start attacking the outer parts. Whereas all these little salt grains, there's a lot more surface area for water molecules to form spheres of hydration around. Okay, so that's one of them. The next one, agitation. your parents or your siblings or whoever, they might be agitated. I might be agitating you too. Sorry, it's my job. Agitation, or we can use another word, stirring, mixing. Scientists love to have specific terms. Okay. Why is it that if you stir a solution, the particles dissolve in it quicker, better, or they just start dissolving? It's because when you have that movement of particles, you can allow for the intermolecular forces to start happening between the different molecules. Okay, so make juice from a powder, or make I don't know, soup broth using soup stock, the powdered stock. When you mix it, you're mixing all the different molecules in water, in the solvent, and then the water can start making hydrogen bonds or ion dipole bonds or dipole-dipole bonds with all the different material within the soup or the juice crystals, powders. Okay, so it's only until you start mixing it that you can have these that you can have these intermolecular forces form, and you can have it dissolve. Okay, the last one, temperature. When you, uh-oh, my thing has frozen, and I'm watching the screen, so I now know that it is frozen. So I'm just going to say, when you mix a solution, you are stirring it mechanically. But when you increase the temperature, you are putting more kinetic energy into the different particles, and they start moving around faster, faster, faster. Okay? If everything's moving around really, really quickly, then there's more chances for them to mix around, for them to have intermolecular forces occur. And if you look at your solubility graphs, you will see that at higher temperatures, virtually all solid ions dissolve better in water, and that's because there's more movement of everything. If everything is moving a lot more, then there's more chance for the intermolecular forces to interact with the different molecules and for things to dissolve. If you look at that solubility table, there is one class of particles that become less soluble as the temperature of water occurs or increases. And the class of molecules is nonpolar molecules that are mostly gas at room temperature. So when carbon dioxide in water is dissolved, yes, it will dissolve. Okay, just thinking about the world's oceans, the plants underwater, they need carbon dioxide. The fish underwater, they need oxygen. Both of those are nonpolar molecules, and they do dissolve in water. But I talk about this all the time. The world's oceans, they're increasing the temperature. That's very bad news for life in the ocean, and that's because when the water temperature increases, the solubility of oxygen and carbon dioxide decreases. The reason why it's opposite, if you have nonpolar oxygen, nonpolar carbon dioxide dissolved in water, the only thing that's keeping it there is London dispersion forces and just the fact that the water's mixing around so much. When the temperature increases, suddenly now there's more kinetic movement of all the different particles, of all the different water, of all the different carbon dioxide, of all the different oxygen. The intermolecular forces is so weak that the carbon dioxide and oxygen will start to, there's nothing holding it there. They're not very dense. Okay, they're very light molecules. They start to rise up to the top because of the separation. You know, that cup that I showed you, things will separate based off of density. Carbon dioxide and oxygen, they're less dense. They don't have, actually I shouldn't say less dense, but there's not much intermolecular forces occurring between them, and so they're just going to float to the top, and they're going to go into the atmosphere, into our gaseous atmosphere. So you have to think about, there's two different environments on planet Earth that animals live in. Either live in a liquid water environment, or they live in an atmospheric, mostly nitrogen environment. Okay, and so um, the way that things interact in water is very different than the way things interact in gas. And most of the oxygen and most of the carbon dioxide that exists in the liquid water part of the world, part of our biosphere, is there because of just mixing. Okay, a waterfall is going to mix oxygen and is going to mix carbon dioxide into the water just based off of that aeration. But given enough time, it will separate based off of density. And if we increase the world's ocean temperature, that separation is going to occur even more. All right, anyways, I'm rambling. I'm sorry, guys. I start talking about the environment and I get way too excited. Good luck. Let me know if you have any questions, and take care. I'm thinking about you guys. I miss you all, and I miss being in the classroom, although I am enjoying teaching in my pajamas. Take care, and yeah, talk to me on Google Classroom.